So welcome to the video on directional derivatives and the gradient. So what we're going to look at here is a function and two things. One, the directional derivative, what that means, we'll cover that first, and then in a little bit something called a gradient. So here's the definition. Let f be a function of two variables and let vector u be decomposed into u1i plus u2j. Where this u is a unit vector. So that's important right there, that this u is a unit vector. And then let the directional derivative at this point, p naught, in the direction of u, be given by this guy right here. So you'll notice this is another limit definition, but this d sub u, that's the directional derivative, similar to our dx, dy, or f sub x, f sub y. But this one is the limit as h approaches 0 when both of these change. The x naught changes in the direction of this u1, and the y naught changes in the direction of this u2. So we go just a little bit, whatever that h is, small amount, in the u1 direction with our x, in the u2 direction, okay, which is the j component, for our y. And then see how that changes. So this is basically the same definition as a derivative, but now instead of limiting only one of these values changing, both of these are changing in the direction of this vector u. Alright, so we have a picture here what that means. So anytime I'm looking at something like this, I can take this point and look at what's going on here. So we'll go ahead and move this point around. So you can tell on this, here I have this plane that's moving. So notice this plane. And this tangent line right here is going to be my directional derivative. So the slope of that tangent line is this directional derivative. So you'll see this little red line at the bottom. That tells me the direction of that unit vector u. And then how the surface changes in that direction. That'll tell me exactly what that value is. So in this case it's negative 0.8 because I'm decreasing in a negative way. And if I just change where that's going to go, so change that plane or that unit vector. So now notice we're pointing this way. So this particular u happens to be 0.6, negative 0.6, 0.75. So now in this case, our derivative is a lot closer to 0. Still negative, but negative 0.1 instead. And so if I just pick any other point that I want, maybe a point up here on the surface, we can look at how our function changes in that direction just by computing this directional derivative right here. Most of the time we're not going to want to use that guy. So I can slide this, see how this guy is changing right there if I want. So you'll notice as this guy changes a little bit, it doesn't like that angle. Let's change this. So I'll move that around this way. Alright, so there's a new directional derivative close to the x direction there. So as we change this, that shows me how that tangent line changes. So how that tangent line changes, that's the slope. So this slope of this tangent line, that gives me this directional derivative right there. If I start, changing this, how that slope of that line changes, okay, from one point to a similar point, you can think of that as your second derivative. So you can do additional derivatives for this. Really, we're just going to stick with one of these. All right. If I want to change my surface, there's another surface right there. And if we're looking at this, I'll just change this angle. Notice how this guy changes as I move that directional derivative around. So we can get values that are flat, values that are steep, all at the same point, just depending on which direction we want to travel in. Alright, so next what we're going to see is, how do I actually compute these things? Because I certainly don't want to use this limit definition every time. So how we compute directional derivatives in a big way is going to be determined by this gradient. So if we can compute a gradient, directional derivative will follow in just a second. So the gradient is going to be denoted by this upside down triangle. That's the Greek letter del. So del f. You'll see that a lot. So most of the time I'll just say gradient rather than del f. But we'll let f be a differentiable function. and so that it has partial derivatives, f sub x and f sub y. And then the gradient is going to be given by this f sub x in the I direction, f sub y in the j direction. So just how this thing changes in the I direction and the j direction. And at a point p naught, the value of the gradient I get just by plugging in those x naught and y naught values. So that's what we get there. A couple other things that we'll see in our homework set. The direction of greatest increase. This is also given by the gradient. So the gradient tells you the direction of the greatest increase, and then this negative value, that gives the direction of the greatest decrease. So sometimes this is known as the steepest ascent and the steepest descent. One other thing, the gradient is normal or orthogonal, perpendicular, whichever term you choose to use, to the contour through x naught, y naught. So this does have a meaning in terms of our contour. So we'll take a look at some contours here next. Alright, so here's an equation I have, one of our paraboloids sitting around like this, and I have its matching contour curve over here. So if I compute the gradient, I see the gradient curve right there, this del f with the upside down triangle. So this thing is always going to be perpendicular to whatever contour I happen to lie on. So if I'm exactly on a contour here, then I'm always going to be perpendicular to this contour when I compute that gradient out at that point. And so this guy right here, if I move it over here, still perpendicular as I get closer to the middle, still perpendicular to those contours at that point. And this tells me the direction of the greatest increase. So you notice this one, it's always pointing in general towards the middle of this thing, because I always want to head up to get to the top of this curve right here. It may not be exactly towards the center. If I'm laying over here on the side, directly towards the center, may not be steepest. Maybe steepest going slightly off center in this direction. So, but that value of steepest descent is given just by that gradient right there. And then the negative of the gradient, that's the steepest descent. So this is the quickest way down the hill. All right, let's take a look at a couple more. So this is a maximum function. If I have a linear function, okay, this is just going to be a plane. Let me change this one as well. So on a plane, we would expect these to always face in the same direction. So no matter where I am, we're always going to be the steepest ascent, it's going to be uphill, steepest descent is downhill, just like this. And it doesn't change because these are always constant. So constant slope, constant gradient right there. Here's a saddle surface, so let's go ahead and do saddle 1. Alright, so on this guy, I can see as I get towards the middle of this saddle, my steepest ascent is going to be right there towards the middle. So that's if I'm on the back side of this guy heading up this way. Alright, so if I'm heading up that curve, I want to go over the top. That's going to be my steepest ascent. If I'm over here on the side, okay, somewhere around this area, I want to go uphill. So the steepest ascent would be this way, descent would be back down towards the middle again. So depending on where you're at, you can get different directions out of this gradient right here. If I'm over here, steepest ascent is going to be uphill this way. In the general direction of this middle. Maybe not exactly through the middle, but in that general direction. So over here, steepest path is going to be up here this way. Alright. The main thing there is that these are always orthogonal to these contour curves. Alright, so contour curves, I can always find something orthogonal to that with the gradient. We'll just show you another one that's fun. Example 2 here. It might come up. I'm going to show this function. This is, I think, some sort of a cosine curve. So you notice this has a lot of dips and valleys in there. So we can see the contour curve coming right there. But each of those whites, those are going to be peaks. A couple of valleys right in there. So anything like this, you notice these are always small. So it's hard to get the exact direction of these when they're so small. You can also normalize this, so the unit normal vector in the gradient. So if I normalize the gradient vector, then I can get this guy out. So here I notice, okay, I'm still perpendicular, still orthogonal to that contour, and this is going to point in the direction uphill towards that peak that's right there. If I'm exactly in the middle, okay, then it depends on where this is going to go. So it's always going to go towards a peak, but I never know exactly which one. Depends on where I'm at. So the further you are downhill, you always point uphill. If you're uphill, by the time I get up here, it gets pretty close to 0 if I don't normalize that. So by the time I get to the top of the hill, the gradient gets pretty close to 0 up there. Alright. So a few properties, and then I think I'll cut the video off and we'll do some examples in the next one. So properties of the gradient. Here we have gradient of a constant is 0. So this never changes, so we'd expect 0. And notice all of these properties are similar to what we have for derivatives. So if you remember derivative properties, these are exactly the same. Linearity, so if I have AF plus BG, and I'm taking the gradient, that's the same as the constant A times gradient of F plus constant B times gradient of G. Product rule, gradient of F times G, gradient of the first times the second plus first times gradient of the second. Same thing there. Quotient rule, same thing, gradient of F divided by G, gradient of the first times the second minus first times gradient of the second, all divided by that denominator squared. So all of these are the same rules that you have for derivatives. So what we see is that the gradient is really going to play the role of a derivative in this thing. A couple more. If I have a power, this notice is the power rule. So the gradient of f to the n, this is going to be n times f to the n minus 1 times that gradient of f. Okay, so there's that power rule that we saw from Calc 1-2. Alright. Directional derivatives can also be computed, so I mentioned this before, and here's how we're going to compute these directional derivatives. You can do the partial of x with respect to y for both the u1 and u2 direction. Alright, so the directional derivative, okay, in the direction of this unit vector u is always going to be the gradient at that value times this unit vector u, or dotted with this unit vector u. So it's always going to be directional derivative at p naught, and then use a dot product with this gradient vector right here. Alright, and it turns out these are partials of f with respect to x in this u1 direction, or times this u1, plus partial with respect to y at that point times the u2. So that's what we'll always get for this directional derivative. Alright, next time we'll start on these examples, so I'll go ahead and cut the video off there. That's sort of the background of where these gradients come from. Really they are sort of analogous to the derivative, and directional derivatives we can also get with this gradient.